Hello and welcome to my speed run presentation for Edexcel Combined Science Physics Paper 6. This goes through things very quickly and is intended as a sort of last minute revision before the exam and should not be the main part of your revision. Topics 7 and 8 dealing with energy, forces and work, where we look mostly at work and power. So stored energy. Gravitational potential energy is energy stored in objects based on their height, and the change in gravitational and potential energy, so delta GPE, equals the mass in kilograms times by the gravitational field strength times by the change in height. So delta G equals m times G times delta H. Remember that delta sign means change. Remember also the gravitational field strength on Earth is 10 newtons per kilogram. Kinetic energy is energy stored in moving objects. So kinetic energy equals half times the mass times the velocity squared. Mass must be in kilograms, the velocity must be in meters per second. So KE equals half times m times v squared. Work done is the energy transferred by a force. It is measured in units of joules, and the equation to calculate it is work done equals force in newtons times distance in meters. Power is the rate at which energy is transferred in units of watts. 1 watt is 1 joule of energy transfer per second, and the equation is power equals work done divided by time. Make sure your time is in seconds. Contact forces are forces where two objects need to be in direct contact for the force to happen. So friction and upthrust are two examples, and then we have normal contact force and normal reaction force. Normal contact force is the force you push on something with, and normal reaction force is the force coming from Newton's third law where it pushes back on you. Non-contact forces include magnetism, electrostatic forces and gravity, where you do not need direct contact. Topic 9, electricity, looking at circuits, current, voltage, resistance and power. In a circuit, current is the flow of charge around that circuit. Now current can either be conventional current, which is positive charge flowing from positive to negative, or it can be considered as electron flow, which is the movement of electrons from negative to positive. A series circuit is one that only has one path for electrons to flow. A parallel circuit is one that has multiple paths for the electrons to flow. Circuits are drawn using circuit symbols. Wires are drawn with a straight line using a ruler, and then we have the symbols you need to know for a switch, a cell, a battery, a lamp, an ammeter, a voltmeter, resistor, variable resistor, diode and LDR. Potential difference or voltage is what pushes electrons around a circuit. It is the energy carried by a current, and it is measured in units called volts. 1 volt equals 1 joule per coulomb. It's measured using a voltmeter. Now voltmeters are connected in parallel to whatever they're measuring the voltage of. Current is the amount of charge flowing through a circuit each second, and it is created by the voltage pushing the electrons around. The units for it are amps, and 1 amp means that 1 coulomb of charge flows every second, and it is measured using an ammeter. And look at the way the ammeters are connected in series with the current they're measuring. Charge is the total amount of electricity that's flowed around a circuit, and it's measured in units of coulombs, capital C. And to calculate it, we do charge equals current times time. Again, make sure time's in seconds. The symbol version of that is Q equals IT, and there is the equation triangle. Energy, the energy transferred by a circuit, energy equals charge times by the potential difference, charge in coulombs, potential difference in volts, E equals Q times V, and again here is the equation triangle. Resistance is the difficulty that electricity has passing through a material, and it is measured in units of ohms. Note the symbol. Conductors have low resistance, whereas insulators have high resistance. This leads to the equation potential difference equals current times voltage, V equals IR. Note the units for each of those things, but I think that equation is better written in this form. Current equals potential difference divided by resistance. So this tells us that the current is bigger if the potential difference or the voltage is higher, and the current is smaller if the resistance is higher. Now a resistor, look at the way it's drawn, has a fixed resistance, and it controls how much current flows to each part of a circuit. The resistance of a circuit is the sum of the individual resistors. So in a series circuit, for example this one, the total resistance here is 75 ohms, because that's what you get if you add up 30, 30 and 15. Here the resistance on this branch is just 30 ohms, because that's what the one resistor says. Here the resistance on that branch is 45 ohms, because you add up the two resistors that are there. Let's look at the resistance in a range of different components. So in a standard resistor, note the symbol there, resistance is fixed at all times, and the graph of current versus potential difference shows direct proportion. Higher voltage leads to higher current. An LDR, light dependent resistor, has high resistance when it's dark, low resistance when it's light. A thermistor, high resistance when it's cold, low resistance when it's hot. A diode has high resistance when current tries to go backwards through it, and low resistance when current flows forwards. So the current versus potential difference graph looks like this, where we get the line sloping up with a positive voltage and flat with a negative voltage, so that means current doesn't flow backwards through it. A filament lamp, note the symbol, has high resistance when it's hot, low resistance when it's colder. So if you look at the graph, it has this flatter section at each end where the resistance is high. In the core practical investigating resistance, we investigated the question, how does change in the potential difference and resistance affect the current? And to do this, we set up each of these different circuits. A standard circuit with a resistor, one with 2 bulbs in series and one with 2 bulbs parallel to each other. And we had a power pack, we set it to 1 volt and recorded the readings on the ammeter and the voltmeter for each thing, then repeat it with each voltage going from 1 volt up to 6 volts, and repeated that with each of the circuits. And we found a few things. First of all was that in general, increasing the voltage increased the current, increasing the resistance decreased the current. We found that on the series circuit, the current was the same the whole way through, but the voltage was shared out equally between the 2 bulbs, so it was half of what was at the power pack. And we found that on the parallel circuit, the voltage was the same at each voltmeter as it was at the power pack, but the current got split out across each branch. Electrical power is the rate of energy transfer measured in units of watts. 1 watt is 1 joule per second, and it's calculated in a few ways. We can either say power equals energy transfer divided by time, or we can say power equals current times potential difference, or we can say power equals current squared times resistance. The equation you use depends on the information you're given in the question. Now, electricity can transfer energy very easily, and to calculate the amount of energy transferred, you do current times potential difference times time. Make sure you get time in seconds, potential difference in volts, current in amps. Now, resistance can also transfer energy in the form of heat. So if we think about an electron traveling through a metal, it bumps into a lot of the atoms on its way, and as it bumps into them, it makes them vibrate a little bit. And those vibrations mean the electron loses some energy, and that also, the vibrations mean that the atoms heat up. Now, if we look at that energy transfer in a bit more detail, always, whenever electrical energy is transferred from one form to another, it transfers into one form plus some thermal energy. Now, that thermal energy is normally wasted. We call that process dissipation. That's the way that energy spreads out and becomes less useful. Now, electricity can be classified as direct current or alternating current. Direct current means the electrons flow a single direction the whole time. Alternating current means the electrons switch backwards and forwards many times each second. If we think about our domestic supply at home, it is alternating current with a frequency of 50 Hertz. That means it switches direction 50 times a second, and a voltage of 230 volts. When our electrical equipment develops faults, it can lead to dangerously high amounts of current that can either cause electric shocks if you touch it, which can be fatal, or it can lead to fires if it gets too hot. So to protect against this, our plugs have fuses in them. Now, the fuse has a thin metal wire in it, and when too much current flows through the wire, it gets too hot and it melts, and that breaks the circuit. Now, the advantage of this is it keeps us safe. The disadvantage is it can be quite slow to happen, so it's not instantaneous, and also you then have to replace them, which is a bit of a faff. An alternative to that is circuit breakers. Now, somewhere in your home you'll have a panel of circuit breakers like that, and if too much current flows through one of your gadgets, one of these switches will flip into the down position and switch off the whole circuit. Now, this happens super quickly, so it keeps you very safe indeed. And also it's very easy to reset when you just flick the switch back up to turn the circuit back on again. Topic 10 to 11. Electromagnetism, where we look at magnetic fields, electromagnetism, the motor effect, and transformers. Magnets and magnetic fields. A magnetic field is the area of magnetic force around a magnet, and we can describe it using magnetic field lines that point from north to south. And you can see those magnetic field lines in this diagram here around a bar magnet. Now, the closer together those lines are, the stronger the magnetic field. So you can see the magnetic field is stronger nearer the poles and weaker away from the poles. Now, a uniform magnetic field can be created by putting the north of one magnet near the south of another, and you can see it's made of these parallel lines of magnetic fields. A permanent magnet is one that is always magnetic, but you can also have temporary magnets that are sometimes magnetic, and induced magnets that are only magnetic when they're near another magnet. And then we have the Earth's geographic north pole. So the Earth itself is a giant magnet, and the geographic North Pole is actually the magnetic South Pole, and the geographic South Pole is the magnetic North Pole. And finally, we can plot out a magnetic field using plotting compasses. So the idea is you put your magnet down, you place a compass around it, and whichever way the compass points, you draw a little arrow, and then you move the compass slightly and you place it again and point where the arrow points. And if you connect all the lines up, you end up tracing out the lines of the magnetic field. Electromagnetism is the idea that when electricity flows through a wire, it creates a magnetic field. In a straight wire, that magnetic field is made of concentric circles, and the direction of that magnetic field, if you point the thumb of your right hand from positive to negative, your fingers will curl round in the direction of the magnetic field. That is the right hand rule. A solenoid is when you coil up a wire with a current running through it, and it makes a magnetic field similar to a bar magnet like this. Note that the magnetic field is weaker outside the coil and much stronger inside the coil. And you can increase the strength of the magnetic field by adding an iron core, which amplifies it, by having more coils of wire, or by increasing the current. Now, we've just seen that a wire with a current through it creates a magnetic field. If we place that wire inside another magnetic field, we get the motor effect. So if we look at the shape of the field around the wire, we see that it's got arrows pointing in the same direction as the magnetic field from the permanent magnet. Now, two fields in the same direction will repel each other, so that will push downwards. Okay. Also, though, if we look at the bottom end here, we can see now the direction of the magnetic field from the wire is pointing in opposite directions to the permanent magnetic field. So that creates an attractive force, again, pulling downwards. So there's an overall force on the wire pushing downwards created by this motor effect. Now, the overall direction of the force can be worked out using Fleming's left-hand rule. So what you do is you point your forefinger in the direction from north to south of the magnetic field, and your second finger in the direction from plus to minus of the current running through the wire, and then you stick your thumb up and that points in the direction that the force is pushing. And we've got an equation too. We say force equals magnetic flux density, that's the strength of the magnetic field, times the current times the length of the wire in meters. So transformers change the voltage of alternating current only. Step-up transformers increase the voltage, step-down transformers decrease the voltage. If we look at the structure of them, we put electricity into the primary coil. That primary coil of wire is wrapped around an iron core, and then the current comes out of the secondary coil at a different voltage. Now, the way they work is that the alternating current in the primary coil creates an alternating magnetic field flipping backwards and forwards. The iron core amplifies that magnetic field, and the magnetic field in that iron core pushes around the electrons in the secondary coil, pushing them backwards and forwards, creating an alternating current in the secondary coil. So we say the magnetic field from the primary coil induces a current in the secondary coil. Now, we have an equation for this. We say that power equals current times voltage, and the power in the primary coil and the secondary coil must be equal to each other. So we end up saying that the primary voltage times the primary current equals the secondary voltage times the secondary current. The national grid is the way that electricity is distributed from where it is made to where it is used. So it is the power lines and the transformers, but it is not the power stations. Electricity is produced from a power station at a voltage of 25,000 volts, 25 kilovolts. It is stepped up by step-up transformers to 400 kilovolts in those high voltage transmission lines you see dotted in the countryside. It is then stepped back down to 230 volts for use in homes, to 11 kilovolts for use in light industry, and to 33 kilovolts for use in heavy industry. Unit 12, the particle model, where we look at density, gas pressure, energy calculations, and the core principles. So density is the amount of mass per unit volume, and the units are grams per centimetre cubed or kilograms per meters cubed. Now, to calculate density, we do mass divided by volume and just make sure the units work. So if your mass is in grams, your volume should be centimeters cubed. If your mass is kilograms, your volume should be meters cubed. Density is increased by the number of particles, so the more particles there are, the higher the density, and the closer together the particles are, the higher the density. And in general, solids are more dense than liquids, liquids are more dense than gases, and that's because the particles get respectively closer together as you go from gas to liquid to solid. We did a core practical on this to determine the density of objects. So with liquids, super easy. We placed a beaker on a mass balance and we zeroed the mass balance. Then we measured 50 centimeters cubed of water from a measuring cylinder, poured it into the beaker and recorded the mass and calculated the density. So the measuring cylinder gave us the volume, the mass balance gave us the mass, and we just did mass divided by volume. With solids, it's a bit more difficult. What we did was we weighed each object and recorded that mass. Then we filled a Eureka can with water and we plopped the object into the Eureka can. Now, the clever thing with the Eureka can is that when you put the water in, so the object in, it forces water out of the spout, and you can collect the water in a measuring cylinder, and the volume of the water collected is the volume of the object. And so then you've got a mass that you recorded, you've now got a volume, so you do mass divided by volume again. Temperature and state changes. Now, thermal energy is the energy stored in the movement of particles. Okay. Temperature is the average movement energy of particles. So at a higher temperature, particles are moving faster, which you can see in this diagram there. Now, specific heat capacity is the energy needed to increase the temperature of 1 kilogram of a substance by 1 degree Celsius, whereas specific latent heat is the energy needed to change the state of 1 kilogram of a substance when it's at its melting point or at its boiling point. So the energy needed to change 1 kilogram of water at 100 degrees Celsius into 1 kilogram of water vapor at 100 degrees Celsius. And we can do some calculations with this idea. So with specific heat capacity, we say that the thermal energy change equals the mass in kilograms times by the specific heat capacity times by the temperature change. Delta Q equals MC delta T. To do the specific latent heat calculations, we say that the thermal energy needed is the mass in kilograms times by the specific latent heat. Q equals M times L. And again, we investigated this with the water core practical. So we investigated how temperature changes as substances are heated. So we took some ice and we put it in a crushed ice, we put it in boiling tube, we measured its temperature. Then we placed it in a beaker of hot water, which was being kept warm with a Bunsen burner, and we recorded the temperature every 30 seconds until 3 minutes after the ice had fully melted. And if we were lucky and we drew a graph of time and temperature, the graph did something like that. And this, and then before it went up again, this flat bit represents what was happening during melting. Then we also heated water with an immersion heater. So we took a polystyrene beaker, we zeroed it on a balance, and we almost filled it with water and recorded the mass of water. Then we placed a beaker inside, or placed the beaker inside a glass beaker to insulate it slightly, and we put a 12-volt immersion heater in there. And then we had a voltmeter and an ammeter connected to it, so we could work out the energy that was being used by the immersion heater. We heated it for 5 minutes, recorded the voltage and current and the final temperature, and we could use that to work out the amount of energy that had flowed, and we could work out the temperature rise, and we could use all that to calculate the specific heat capacity of the water. Gas temperature and pressure. Now, as we've already seen, at a higher temperature, the particles are moving faster. Now, with a gas, the pressure of a gas is caused by particles hitting the surface of a container. So at a higher temperature, because the particles are moving faster, they hit the surface more often, and so that means they have a higher pressure. And we get a graph that looks like this with a direct proportion showing as temperature increases, the pressure increases too. Now, if you cool something down, the particles move more slowly. Cool it enough, the particles stop moving completely. This leads to the idea of absolute zero, or 0 Kelvin, which is minus 273 degrees Celsius, or 0 K. Now, that is the temperature when particles are not moving at all. That is the coldest possible temperature. You cannot get colder than that. At that coldest possible temperature, the pressure is 0, because the particles aren't moving, so they can't hit the walls of a container. To convert between Kelvin and Celsius, to turn Kelvin into Celsius, you add, you take away 273. To turn Celsius into Kelvin, you add 273. Unit 13, forces of matter, where we look at springs and spring calculation. When any object bends or stretches, you require two forces acting in opposite directions. Now, that stretch, or deformation as we could call it, is elastic if the object returns to its original shape after you stop applying the forces, or inelastic if it does not return to its original shape. The extension of a spring is how far it stretches when a force is applied, and what we find is that if you graph the force in newtons versus the extension, with all springs you get a section here where it's in direct proportion, you get a nice straight line, and then it becomes non-linear after that. And we investigated springs using this core practical, which was to investigate how does the force applied to a spring affect its extension. So we hung a spring from a clamp stand, and then we clamped a meter ruler so that the 0 on the meter ruler was level with the bottom of the spring. Then we hung a 100-gram mass from the spring and recorded the extension on the ruler. Then we repeated that adding masses all the way up to 1,000 grams, again recording the extension each time. And they repeated that with a range of different springs of different strengths, and maybe with a rubber band as well. And we found that with different springs, the same force led to different amounts of extension. The spring constant of a spring is a measure of the strength of that spring, and it has units of newtons per meter. In our graph of the force versus the extension, the spring constant is the gradient of that graph. Remember, to calculate gradient, you do the change in y divided by the change in x. Hooke's law tells us that the force equals spring constant in newtons per meter times by the extension, so F equals K times X, and the energy transferred by a spring in joules is half times by the spring constant times by the extension squared. And just a quick reminder of all the formulas that could come up in the exam. So kinetic energy equals half times mass times velocity squared. Gravitational potential energy change is mass times gravitational field strength times height change. Work done equals force times distance. Power equals work done divided by time. Charge equals current times time. Energy equals charge times potential difference. Potential difference equals current times resistance. Power equals current times potential difference. Power also equals current squared times resistance. Force equals magnetic flux density times current times length. Primary voltage times primary current equals secondary voltage times secondary current. Density equals mass divided by volume. Thermal energy change equals mass times specific capacity times temperature change. Thermal energy equals mass times specific latent heat. Force equals spring constant times extension, and energy transferred by stretching is half times spring constant times extension squared. Note the ones that have the star here. These will be in the formula sheet at the back of the paper and will not need memorizing. Also, you should get in the habit of using success D to help yourself work through the calculation problem. So S, star the target, U, underline the values, C, copy out the values, C, convert the units, E, write out the equation, rearrange if you need to, S, substitute the values, S, solve, and D, don't forget the units. Thank you for listening. The end.